9 volts, and we have another voltage regulator that's being used to set down to 5 volts to power the rest of the computer systems. The reason we did this instead of one single bus was that as we were trying to do that, we placed too much stress into one single point. And by doing this way, it was actually moving the power flow throughout the whole system.
So yeah, it uses a 16.8 volt battery when it's fully charged, and when it's fully discharged, it's 14 volts. So using that as a single power bus, we're able to power all the electronics and motors on board. So this kind of provides the backbone of everything that's going on here, our processing hardware. So the Pixhawk flight controller is it's an autopilot software that basically controls the stability of the aircraft. For when we send it commands, movement commands. We develop everything on the Raspberry Pi here, and we send in movement commands to the Pixhawk, which in turn delivers the drone to where we want it to. Yeah, the Pixhawk outputs PWM signals, which are used to drive the motors here, and it also has a suite of onboard sensors, accelerometers, barometer, compasses, that sort of thing, in order to kind of tell where it is at any given moment. And it's got its own operating system called Autopilot, which is developed for autonomous robot vehicles. It could be used for a quadcopter or for a submarine or for little RC cars and stuff. But it's got a very robust software on board and a lot of parameters and sorts of things that we can manipulate to make sure everything stays safe and make sure that it does what we want it to do. And then last on the right here, we have this Pixie Cam 5. It's a little camera with an onboard processor and a color-based algorithm. So as part of our mission, we do a specific training. So we have taught this camera this particular color combination. And when it's in the air, it looks down and it sees that, it outputs blocks, the coordinates of where this object is. Sends that back to the Raspberry Pi. The Raspberry Pi determines what the best course of action is, sends that to the flight controller, and it translates it to real-time flight.
Even though it's just a fixed other so in our higher bank computers can handle that as well. But we use this, that way we don't strain the rest of the
So a little demo video of the attendance. We're going to show you how it's working in real life right here too. So we created this primarily using 3D printed components. So you see it's got these two grasping arms right here. It's got a 3-to-1 gear ratio that's driven by the stepper motor. And above it all, it's now some of the components that we use in there. So we use this design we call the rigid double band grasper in lieu of a traditional claw, because we, in case anything is not quite accurate, we don't want to damage the light bulb. So this allows for a little bit more flexibility, a little bit more surface area around the whole bulb. Yeah, and so we have a single step motor driving this from a smaller gear. So it's 3-to-1 ratio, steps up the torque, so that we're able to manipulate the bulb. So this is really important because it's showing the way this machine is interacting with its environment and in a tangible way. So here's some components that we use for that. 3D printing allowed for rapid prototyping, and we had a lot of revisions to some of these pieces, and it would not have been possible without this technology. Created at our very own HTC Print Lab. So some of the pieces that might be going around, we have the attendance base right here, houses all the electronics at the top. At the very top of the device, we have this battery shelf, which is right here. Normally a drone battery goes on the bottom, but because of all this extra stuff, we had to make some concessions and work around that. And then right here is the lower appendage where we have this, where the servo is mounted, right here, and then also these claws that are held in there with bearings.
All right, so for the software development side of the project, we decided to go with the Raspberry Pi 3 because it can be an onboard operating system.
Full desktop.
Which allows us to remote into it via SSH secure shell protocol, so we can monitor and send commands from wirelessly through a computer, such as the way I did it to do the light bulb demonstration. And so with the Linux operating system that the Raspberry Pi has, It comes pre-installed with Python libraries and dependencies that we are able to import. We used to also import other dependencies for the external components, hardware components that we use. A lot for a way that we can integrate all the hardware components into one program, one Python program. For instance, some of those dependencies are drone kit right there is what we use to basically develop movement commands for the PixHawk controller. Piximon is a library dependency that allows us to export the coordinates of the image processor and feed that to the Raspberry Pi, which in turn feeds it to movement commands of the PixHawk.
This is the GUI for Piximon right here. We can use it to train the colors, and you guys can see right there, it identifies some blocks in there.
And then some other things we used a couple different ground control stations, Q ground control and mission planner, which allows us to change the parameters of the basically the flight characteristics of the PixHawk itself. And
these are all open source software. There's a large community of hobbyists and others that are developing these types of projects, and yeah, we have ready access to lots of these autonomous software and the flight stacks and everything that goes into this.
yeah, so basically we were able to heavily customize each of the source code for each individual hardware component and compile it into one overall mission program.
So here is a flowchart detailing some of the communication protocols used within the whole system. So right here we see kind of the backbone, which we talked about earlier, the PixHawk, the Raspberry Pi, and the Pixie camera. So those three are connected through serial, and through USB. They're all connected, and they communicate with each other on an internal network. And everything else is kind of peripheral. So you see off the Raspberry Pi, it talks to the motor shield, which then drives the motors, the stepper and the servo. It also has this wireless connection to the computer where we our ground control we get into it. Over here on the PixHawk, it's connected to an RC receiver and our GPS system. And then that itself outputs PWM signals to the electronic speed controllers and the four motors for flying.
As you can see, even though it's an autonomous system, we still have our safety feature called the RC transmitter. So therefore, like anytime that we do lose control or we lose communication, we're ready to take control of the whole system on the spot.
And there are very robust safety features built into the PixHawk. So, for example, it won't arm unless all the sensors are giving proper readings, unless it has a good GPS lock, and if there is an RC transmitter attached. Because we would hit it fall out of the sky or go out of range and just fly away or something. So this is the view from Chris's computer over here whenever we're flying.
Yeah, so this is after I've already established connection through SSH into the Raspberry Pi remotely. And then I load up the Python program with a couple different modular parameters that we can change on the fly. And then, so right now what it's doing is it's physically connecting the Raspberry Pi to the PixHawk. And it's doing a couple different parameter checks, giving battery levels, see if it's armable, or the GPS lock is.
Make sure the sensors are healthy. And it also tells us just the flight mode right now, in this case it's the stabilized mode, and then it goes into the phase of arming the motors and checking that device is ready to go.
So then after it's armed, initiates the takeoff, and you can see here it's currently rising in altitude, and then gives you a notification that it has reached it. And now the going to function represents the drone flying to the destination, which is this platform right here.
We've had a GPS coordinates, and it uses that to track, within rough GPS accuracy of where it is. Once it gets there, we have a function here called auto yaw, which makes it face north, which we found helps us in the landing, kind of keep everything a little more regular.
And then a little bit later, once we get to here, this is the point where it's now hovering over the signature. So the image processor kicks into gear, gives us the coordinates of that signature, and then the Raspberry Pi processes it, feeds it to the PixHawk, and is able to precisely land on the board here.
Yeah, so this is it. It's basically telling us that it's found the signature and that it is performing.
That it's tracking.
And then it does that until it has landed safely, and it needs the mode to disarm, and that's the completion of the mission that we gave it right here. So without further ado, here is a video of the complete task. So here it is going to screw in this light bulb, and it's going to fly and it's going to land on this pad right here. So when we were making this, we were hoping for enough accuracy to be able to land on the light bulb, unscrew it, and then fly it away. We found some limitations in there, mainly in the environment. The wind changes in air humidity, the sunlight can all have effects on the sensors on board, which we didn't anticipate. And also some of the limitations of the hardware, just the size, the geometry of it, made sort of that fine motor control a little bit more difficult. So this is fully autonomous flight right here, and even when it's landing. But even in the best case scenario, we get about 30 centimeters of accuracy.
Yeah, and like I said, we estimate that we can make it even more accurate by saying improving this to a hexcopter, adding more rotors, which in turn adds more stability.
More stable, more rotors.
And then maybe a different sensor instead of an image recognition, maybe sonar or radar kind of detection.
We're going into the precision land mode right here. Yeah, so increasing it would be kind of beyond the scope of this project, but it could be made to be more precise. However, this drone could act as a general platform for any number of services. For example, Amazon and Walmart are working on delivery drones and packages. They're using drones in precision agriculture and topographical surveys. You could even use this to replace, say the bulb on top of a radio tower. Instead of having to pay a guy to climb up the tower and change that dangerous work, you could have a machine do that and replace that job.
Mm-hmm.
So, this is our autonomous drone platform. Anyone have any questions?
You explained it that well.
Yeah, I have a question that might not be right, but what's the point of the wood structure, right? Like, I really like the concept, right? I think it has a lot of potential, so that's great. And of course, there's a lot of thought and details that go into this, and so I congratulate you for that. This is amazing. I'm just trying to understand a little bit more the practicality of the structure itself, and the way that platform adds to the drone, right?
Sure. So when the drone is on its own, it's like this. As you can see, the appendage, it kind of is suspended like that. And we did that at just the right height so that when it's around the light bulb right there, it'll grab onto it at the perfect height to get the most surface area on the bulb. So as a result, we calculate, okay, with this thing adds a couple inches, with this adds a couple inches, it needs to be this high off the ground, and we found that we needed some support structure to hold it up above that to be suspended, because if we landed it, if it was sitting on top of this thing, it would just crush it.
Could you build some legs onto it that
Sure.
can morph
Yeah.
into?
We talked about a couple different designs for that. We were originally looking at maybe some 3D printed ones, because people do build landing gear for drones that way. We're also looking into people use carbon fiber for like hobby helicopters and that sort of thing. So there are materials out there that would be lighter and that would probably be better than this. But given our time and monetary constraints, we found this wood to be pretty good for that purpose. And
Plus we had some limitations in weight for the motors, and going with this design for the landing gear allowed us to stay within the weight limitations to complete the task. No, it doesn't look as pretty as it could.
That's exactly as it is.
We should have spray painted it. Cool.
Any other questions for this talk?
So tell me a little bit more about the 3D printed parts that you have in there. So choice of polymer and time of construction and cost.
Sure. So we printed it using the 3D printers I have available at the school here. It was all printed using PLA plastic.
So it's free to print the.
Yeah, we decided to provide the school the PLA, and all of the pieces were designed using AutoCAD.
Okay. So why didn't you choose another polymer that has better mechanical strength or properties? PLA is it's not the most sturdy of polymers.
Sure. So for what we're doing right here, we needed it to be sturdy enough to kind of hold its position, but it's not supposed to be going under too much stress and getting beat up too much. And
lighter weight too.
Yeah. frankly, I don't know much about the types of 3D printer polymers. PLA is what I've always used for that, and it has served us well for this project. Yeah, I'm not 3D printing isn't necessarily my strong suit, but I was able to use it for this project. Any other questions?
I have one question. If you are trying to change a light bulb in the eye, wouldn't that light bulb be turning upside down? Or you have to
In a practical situation, yeah.
But there are some that aren't, say such as the ones on top of radio towers that are just kind of facing up. Maybe that would.
Yeah, again, it's supposed to be more of a proof of concept, not to be a.
So yeah, so what's neat about the design, we can easily swap this lower finish design out for something else, and it can be a delivery drone, say fertilizers for farming, kind of.
Yeah. So it's always something.
We just chose light bulb just to proof of concept.
It is an interaction with the environment. Anyway, thank you.